B3, right? From GPS packet 11. So, um, in this case, right, what we're, it was only requested to do part E, but I'm going to do F as well, kind of just to prove a point, right, of how diluting something, still has an effect on the pH, and everything, even though, right, like the total amount of the weak acid, right, in terms of moles is the same, right? The concentration is actually the thing that's important because, right, when we talk about equilibrium. So in this case, right, what we're looking at is acetylsalicylic acid, right? So the active component of aspirin. And so the first part, right, is calculating the pH of the solution that you make when you dissolve 500 milligrams of acetylsalicylic acid in water and diluting to 50 milliliters. So the first thing that we need to do is we need to figure out what the concentration is of the acetylsalicylic acid. So first, let's calculate the number of moles, right? So the number of moles is going to be equal to 0.500 grams divided by the molecular weight. And the molecular weight is 1.01 plus 12.01 times 9 plus 7 times 1.01 plus 4 times 16. So that gives us 180.17 grams per mole. And so grams cancel, right? Moles go up top. And so what we have is 0.5 divided by 180.17. And so that comes out to being 0.00278 moles, right? And so we can get the concentration then. I'm just going to simply simplify that down to HA. And so that's just simply going to be then the number of moles. So 0.00278 moles divided by 0.05 liters. So what we get there is 0.00278 divided by 0.05, which is 0.0556 molarity, right? So that's the concentration. So if we were set up the acid dissociation reaction, right? So that's just simply HA aqueous plus H2O liquid forms A minus aqueous plus H3O plus aqueous, and get our ice table going. So we start off with 0.0556 molarity of HA throughout the H2O. We don't care about that. And then we have A minus, which starts off at 0 in that case. For HA, right, we're going to lose one equivalent of X. We're going to gain one equivalent of X for A minus, one equivalent of X for H3O plus. So that means at the end we have 0.0556 minus X. And then for A minus, right, we have X, and H3O plus, we have X in that case. All right, so we can set up our equilibrium expression. So that's going to be Ka is equal to the concentration of A minus times the concentration of H3O plus over the concentration of HA. And so if I plug in our n values that we have right here, right, so that just simply becomes x squared over 0.0556 minus x, and that's going to be equal to the Ka value, which is 3.0 times 10 to the negative 4 in this case. So what we can do is we can try out the 5% approximation. So, right, so we're just going to disregard that x. And so what'll that give us is going to be then x squared is equal to 3 times 10 to the negative 4 times 0.0556, which is 1.668 times 10 to the negative 5th. So what that gives us then, if we take the square root of this all, is x is equal to 0.00408 in this case. Right, and so what we can check then is whether that's within or outside of the 5% rule. So we take then 0.00408, divide that by the initial concentration of HA, which is 0.0556 times 100, and so what I got was 7.3%, right? So we're outside of that range, so we can't use the 5% approximation in this case. But we have like a rough idea, right, of where the numbers are going to be at in these scenarios. So that x has to come back. So minus x. So now we have to do the quadratic route, and so we're going to take that, and so we have then x squared is equal to what was that again? 0.00. Oh, wait, I already have it in my calculator, right? So that's 1.668 times 10 to the negative fifth minus 3.0 times 10 to the negative 4x. And so we bring all of that stuff onto the same side and set it equal to 0. What we then have is x squared plus 3.0 times 10 to the negative 4x minus 1.668 times 10 to the negative fifth is equal to 0. And so then x in this case is going to be equal to, go use my solver function on my calculator. So we have x squared plus 3 times 10 to the negative 4x minus 1.668 10 to the negative fifth. And we solve for that. And then what we get is 0.00394 in this case. Make those look like actual zeros. Right? And so that's going to be the concentration of H3O plus, right? And so if we just do a check, right, in terms of the percent ionization rate, so take that, divide that by 0.0556, multiply that by 100, right? We're still coming in at like 7.1%. So again, right, you have to, you can't use the 5% rule in this case, right? You should use the quadratic equation, right, and do it the proper way. So now to figure out the pH, all we do is we just simply plug in that H3O plus value, right? So now we have the pH is equal to the negative log of 0.00394, and that is going to be equal to negative log of 0.00394 is 2.41 is what I got, which I think matches what the key is. Yeah, 2.41. Right? So we're good there. So now the next part of the question, right, was if you take that same amount, right, same number of moles of acetylsalicylic acid, and now you dilute it into a liter of water, right? So now, we're going from something that was in 50 milliliters to a liter of water, and we can calculate what that pH is then there. Because again, right, it's concentration that matters for the pH. It isn't, how many, the actual number of moles that are present in that solution. And so in this case, right, so we already calculated how many moles we have in this scenario, so we just need to calculate the new HA. And so that's going to be 0.00278 moles divided by 1 liter. And so that comes out to being 0.00278 molarity in this case. And so now if we set up, our ice table, right? So we have HA aqueous plus H2O liquid, and is in equilibrium with A minus aqueous plus H3O plus aqueous. So our ice table, what we have is initially 0.00278 molarity, and then 0 of the A minus, 0 of the H0 plus, right? We lose X, we gain X, we gain X. So we have 0.00278 molarity, and then X, and then X. And so now if we set up our Ka expression, right, what we have is the Ka is equal to X squared over 0.00278 minus X. I forgot the minus X right there. In this case, right? And that's going to be equal to 3.0 times 10 to the negative 4. Now, I already know that the 5% approximation isn't going to work. And that has to do with the fact that if, it didn't work in the previous one where everything was more concentrated, I know then that at a lower concentration, that also isn't going to then work. And the reason that I know that, right, is that if we look at the order of magnitude that we're at, right, for the concentration of the starting material, it's starting to be roughly the same order of magnitude that the Ka is in these cases, right? And so if you start multiplying those two together, that means then that the amount of the starting material is going to get ionized more. Right, because as you're going to lower and lower concentrations, because you're only going to make so much H3O plus, but comparatively, right, you're not going to be shifting you're not going to shift the amount of like the pH to be at a ridiculously low amount, right? The furthest low, like the lowest that it could go hypothetically, right, would be something that's like close to 7, right, like 6.99 to the infinity or whatever, right, if you're adding a weak acid, right, in these scenarios. But you're going to start hitting essentially a plateau with the fact that the Ka is 3.0 times 10 to the negative 4 in these cases, right? And so then you're just getting then how much of that is getting ionized in those scenarios. And so that's why I know, right, that the 5% rule isn't going to matter. And I'll show it to you in a second, but we can just go through and then just do the calculation. So, right, we take this and then we convert it into the quadratic stuff, right? So I'm going to bring that over. So we have, what is that? 0.00278 times 3 times 10 to the negative 4 is 8.34 times 10 to the negative 7 minus 3.0 times 10 to the negative 4x. And so we set all of that equal to 0. So we get x squared plus 3.0 times 10 to the negative 4x minus 8.34 times 10 to the negative 7 is equal to 0. And so what that gives us then is that x is equal to, right, so math solver, x squared plus 3 times 10 to the negative 4x minus 8.34 times 10 to the negative 7. Do solver, what we get is 7.75 times 10 to the negative 4 in this scenario. Right? So, right, so we have that value right there. And so now if we do, the percent ionization calculation, in this case, right, so I take that value, divide that by 0.00278, multiply that by 100, right, we're at roughly 28% ionized, right? So that's a huge jump. Beforehand, we were at like 7% ionized, right? Now we're at 28%. And so that's the thing, right? So as you go to lower concentrations, the percent ionization is going to go up. It's not going to go to 100%, obviously. But it's going to go up a fair amount. And so as the concentration, as the order of magnitude of the concentration of the weak acid, in this case right here, right, starts to get close to the order of magnitude of the Ka value, that's when, the 5% rule starts to break down in those cases, right? Because right now we're at like, 2.78 times 10 to the negative 3 is the concentration, right? So we're one order of magnitude away roughly. And so that, becomes a problem. Beforehand, when we were at 0.0556, right, we were about, a little bit over 2 orders of magnitude away, right? We were at, 5.56 times 10 to the negative 2. And even then, right, we were like still above the 5% rule, right? We were still at the cusp in that case. And so, that's the thing to think about in terms of kind of saving yourself the time, right, is looking at that. If this was, a scenario where the weak acid had a Ka of, times 10 to the negative 10, you're not gonna hit, right, that 5% rule is going to be completely valid in that case, because again, you're pretty far away, right? Like you have to have a super dilute solution to get there, right? We're talking about the nanomolar range, right, like times 10 to the negative 9 if your K is at like times 10 to the negative 10, to for it to not work. And that's pretty low, right? That's not where we're typically working at here. And so that's a thing to think about, right? In terms of like a tip, in terms of like, spending your time the way that you should. But anyways, let's wrap this up. This is the last part. So pH then is going to be equal to the negative log of 7.75 times 10 to the negative 4. And so that's equal to 7.75 times 10 to the negative 4, 3.11. right? So that's what the pH is and the